Then last time we have talked about the definition of angular velocity, and then let's have a look how it is related to the speed of the object in a circular motion. So normally we know that if let me draw it. If an object is moving faster in a circle, okay, so it should have a faster speed. So, but how we can relate it with the angular velocity omega? So let's first of all, so this is a relation between the translation motion and the rotation motion. So between the speed and the angular speed, or we call it angular velocity. So first of all, in mathematics, in a zeta. So let's say that if this angle is theta, and then the radius is r, so this length, the arc length s, and then you know that there's a formula relating the arc length with the radius and then the angle. But this angle should be in radian. Okay, that's what you have learned in mathematics already. So and then how can we make use of this relation? So let's say if the particle at time equals 0 is here, and at time equal t, the particle is here. So the distance traveled by particle is s. If we divide both sides by t, and then we can get the distance divided by time, that is the speed, and then the theta divided by time, that is the definition of angular speed. So it's r omega. Yeah, that's the formula. Okay, that's the formula for the angular, the relation between the angular speed and then the speed of the object in a circular motion. So let's give you one example. So let me still using the clock for example. So let's say I'll just give you an example for a second hand. Okay. So we know that the second hand will travel a circle in 1 minute. Okay. That means the period is 1 minute. So let's find the angular speed of this rotation motion. So it's 2 pi over period, and then one period is 60 seconds. Of course, you should know that the SI unit of time is second. So and then use your calculator and then divide 2 pi divided by 60. Uh, you can keep it pi over 30 first, or you just keep it with 2SF or 3SF. Then you should know that unit should be radian per second. Okay. Let's say if the length of this second hand to be maybe 2 cm. So we want to find the speed at the tip of the second hand. So the distance between the tip to the center of the circle is 2 cm. So we use the formula V equal R omega. R is the distance between the particle to the center of the circle, and the angular speed omega. So and then we substitute all the values inside. So R is 2 over 100 and then times pi over 30. So that's your answer. Or in terms of meter per second, it will be 2 times 1 times 10 to the power negative 3 meter per second. Okay, that's how we relate the radius and the speed and the angular speed. So that is very important formula. Oh yeah, so we have learned there's another formula for the omega last time. So yeah, therefore actually we can we reformulate this for this one, and we know that the omega angular speed can be written as 2 pi over period. So the speed can also written as 2 pi r over period. So there's another way to understand this formula. 2 pi r is the circumference of the circle. Okay, and then t is the period. There's a time to travel a whole circle. So distance over time then give you the speed. Okay, so that's how you can understand this formula. And then, okay, so we're finished talking about this one, and then let's go on to a more challenging or more conceptual topic, that is the acceleration of the circle motion. So if the object, actually can I insert a circle here? If an object is moving in a circle, oh sorry, so ugly, sorry. Which one? Oh no. Never mind. Maybe. Okay. So sorry. I draw it by hand. Okay. So to save time. So if an object is moving in a circle, okay, is there any acceleration? So what you should have learned about the definition of acceleration long time before. So that is change in velocity divided by change in time. So let's say if in this case the object is moving with constant angular speed, and of course the radius does not change. So if it is moving at constant angular speed, then by v equal r omega, the v should not change also. So this should also be a constant. So does it mean that the velocity is also a constant? No. In this formula, the v just gives you the magnitude, but it doesn't say anything about the direction. So the velocity is actually not a constant. But why? You know that in different positions, the particle has different direction of motion. Those arrows I draw here is the direction of the motion. And then the direction of the velocity changes with time. And you know that velocity is a vector. So that means the velocity also changes. It keeps changing during the motion. So that means the change in velocity is not zero. Therefore, the acceleration is also not zero. Okay, that's the concept I want you to know about. So in a uniform, okay, let me use a test box. So in a uniform circular motion, the uniform means that it has a constant speed. But when you say it is constant speed, you also mean that it has constant angular speed. So the velocity keeps changing because the direction keeps changing. Okay. So therefore, there is an acceleration, or the acceleration is not zero in a circular motion. So, okay. So in next lesson, okay, we will talk about how to derive the formula of the acceleration. See you.